summary lecture here. I will speak not only about all this object, but also about relations among them. So, first of all, I will speak about different systems of numeration or different expansions I will speak about different expansions for real numbers and some special expansions which are generated by iterative function systems, and how I will speak about how the theory, the metric or ergodic theory of dynamical system can be used to develop the corresponding metric theory of different expansions. I would like to mention that the finite IFS is more or less known objects, and fractal properties of corresponding interactors and measures are more or less widely known. And it is also known that the methods from ergodic theory of dynamical system and statistical physics are of great importance to study such an object. But the corresponding infinite IFS is essentially less investigated. And today I'll speak about several new phenomena related to infinite linear IFS. This phenomena will be related to the Hausdorff dimension of the corresponding attractors. For instance, even for the simplest problem for the calculation of the counter-like sets generated by infinitely many contractions, the corresponding equation for finite case is a root of such an equation, but for infinite dimensional case, this assertion doesn't hold. I would like to also mention that many famous expansion with infinite alchemy, maybe the most known example is the so-called continuous fraction expansion. I will discuss two new phenomena connected to continuous fraction expansion. Another one, the generalized Lurd expansions, which can be considered as a linearized version of continuous fraction expansion, also lead to some new phenomena. Okay, I will define several known definitions so that F1, F2, Fn be a collection of contraction mechanisms acting in Rn, and for any subset E, we can define the transformation F in the following way. So it is rather trivial that if all these mechanisms are contractions, then F is a contraction in the complete metric space where ρh is a so-called Hausdorff metric.
The number of maps is dimension.
Not necessary. It's just a coincidence, yes. There are no connection between the dimension of the space and the number of contraction maps. It's just a misprint. Okay, in such a case, there exists a unique set, compact set S, such that which is invariant under F. And if all these transformations are similarity mappings with the corresponding ratios, then the corresponding invariant set is said to be self-similar, and the similarity dimension is defined to be the unique positive root of this equation. And it is also well known that under the so-called open set condition, the classical Hausdorff with equation dimension of this attractor coincide with the similarity dimension. Okay, and today, now I will speak about the coding space on attractors of iterative function system. So we start with invariant set S, which is attractor of the corresponding IFS, and we define the decomposition of the attractor into the so-called cylinders in the following way. This is the cylinders of the first rank. Here we define the cylinder of the second rank, and by induction we obtain the notion of cylindrical set of any finite rank. And it is rather clear that this system of cylindrical set generates a decomposition of the attractor. And for any sequence of indices, there exists a sequence of embedding cylindrical set, such that there exists only unique point from the attractor. And vice versa, for any x from the attractor, there exists a sequence of indices such that this relation holds. For simplicity, if all of fi of x is defined as follows, then the corresponding attractor coincides with the unit interval, and the f expansion coincides with the classical n-adic expansion. In such a case, we obtain the so-called Q expansion. And having a sequence of independent, identically distributed random variables, which takes values from the set with corresponding probabilities, and let fi be similarity matrix. Then the corresponding probability distribution of random variable psi is said to be self-similar measure related to the list. The initial list is a list of contraction, and here the probability list. Actually, this attractor is just a spectrum, or spectrum means a minimal dimensional support, so minimum topological support of the measure. And a lot of interesting properties of the attractor can be defined via behavior of the corresponding measure. Here we discuss only IID case. And to study rather delicate properties of the measure and sets, usually probabilities define the so-called notion of the Hausdorff, alpha-dimensional Hausdorff measure, but here we generalize a little bit this notion in the following sense. So let phi be a fine covering system of set C. So the family of subset from C such that for any arbitrary subset E and for any positive number, there exists an at most countable covering of this set by elements from this fixed family. And after that we use the standard procedure. Here the formula is almost the same as in the definition of the Hausdorff dimension, alpha-dimensional Hausdorff measure. But the unique difference is that all this EJ should be from a given family phi.
What is absolute value of EG?
It's just a diameter of the set. So sum distances of points. And in absolutely similar way, we define the Hausdorff dimension of a set E with respect to the family phi. And this number is said to be the Hausdorff dimension of a set E with respect to fine covering family phi. In one-dimensional case where C coincides with the unit interval, and if phi consists of all possible subsets, then we get the traditional definition of the Hausdorff-Bezikovich dimension of a set E. And this was the definition of the Hausdorff dimension of the set. But here we define more delicate object, the so-called Hausdorff dimension of probability measure. So we consider all the family of all possible supports, not necessarily closed sets. For any support where we should calculate the Hausdorff dimension and consider the infimum. Actually, this number could be considered as a minimal dimensional support, and there exists a set such that the Hausdorff dimension of this set coincides with this number. Generally speaking, this set is essentially small than the topological support. Okay, and now I will define more or less new notion, the notion of fractal faithfulness of covering families. So let F be an IFS, and let S be an attractor of this IFS. Let phi be a fine covering family of cylinders. Then, such a family is said to be faithful for the Hausdorff dimension calculation on the attractor S. If the following relation holds, for any subset from that vector. And correspondingly, phi is said to be non-faithful. Is said to be non-faithful if there exists a special subset such that the classical Hausdorff dimension of a set is actually strictly less than the Hausdorff dimension with respect to a family phi. I would like to mention that it is extremely useful to obtain information about the faithfulness, because it is essentially easier to calculate dimension if you consider covering by using the countable family of cylinders, not in other sets. I would like to mention that if Fi or Fi satisfies the open set condition, then properties of the attractor and measures are more or less well established. But for non-open set condition case, properties of the corresponding measure almost nothing about fractal properties. Even in one-dimensional case, and even in the family of two contraction, we obtain this measure is known to be the infield Bernoulli convolution, and a lot of paper devoted to this problem, and a lot of problems appear even for the unique case where lambda is a golden ratio. Okay, and the main phenomena I will speak about related in the following generalization of the finite case. So starting from the finite list of contraction and with a finite list of probabilities, we have several ways how to generalize the family of the corresponding measures. The first, and rather natural, consider to infinite IFS. The second way is to allow to change the system of n contraction method and probability list and every stage of contraction. So at any stage you obtain a finite list, but from step by step you apply new contraction ranges. And the third way is to allow to choose the number of contraction, including infinitely many contractions at any stage of contraction. Maybe I will already mention that the most famous situation leads to the continued fraction expansion for real numbers. And having such a contraction, we obtain the so-called continuous fraction expansion for real numbers, where all digits are positive integers. Actually, I would like to mention that this maybe the most known expansion for real numbers, and nevertheless, two new phenomena will be discussed today. The first problem is the so-called problem of dimensional theory of continued fraction expansion. A lot of research papers were devoted to this problem, but even for the case, if you try to calculate the Hausdorff dimension of sets of those real numbers, where you use only two digits, 1 and 2, to obtain exact dimension of such a set is still open. But in the paper by Kyiv picture, it has been shown that the family of continued fraction cylinders is faithful but not for all sets, but for special sets under the following assumptions. So if for any point x from a set E, such a value tends to some finite non-zero constant, then to calculate the Hausdorff dimension of a set E, it is enough to cover the set by continued fraction cylinders. But in general case, this the generalization and the faithfulness does not hold. And it is more or less a recent result which obtained in collaboration with Yuval Peres from Microsoft Research. So the file-covering family phi of cylinders generated by continuum fraction expansion is not faceless. Moreover, there exists a set E. I would like to mention that the set E is a set of those real numbers which are x defined in continuum fraction expansion and digit of the corresponding place belong to a special subset from positive integers. So the set defined actually directly in the terms of continuum fraction expansions. And we construct a special subset such that classical Hausdorff dimension of a set E is equal to 0, but if you calculate the Hausdorff dimension with respect to the family of cylindrical set, then the Hausdorff dimension will be at least 1/2. But until now, we don't know whether the following conjecture is true. If the set E is large enough, so that the Hausdorff dimension is larger than 1/2, then for any set which under such an assumption, the following relation holds. The following object is also called random continued fractions. We consider the case where x1, x2, xk, and so on are independent random variables. I would like to mention that if x1, x2, xk, and so on are independent and identically distributed, then properties of these random variables is more or less known. Why? Because actually it is known that such a measure is invariant and ergodic with respect to one-sided shift transformation. And on the other hand, it is known that Gauss measure is also have such a property. And it is known if you have two invariant measures which are ergodic, then such measures are either singular or they should coincide. And so the singularity can be obtained more or less easy way. But in, like I said, 12 years ago, in the paper by Benji Weiss, Yuri Kiefer, and Yuval Perez, was investigated more delicate properties of such an object, and they proved the so-called dimensional gap. More exactly, they proved that there exists a positive number epsilon 0, such that for any possible distribution of x1, x2, and so on for xk, the Hausdorff dimension of the corresponding measure is strictly less than this positive constant, which is strictly less than 1. This is the so-called dimensional gap. For general independent case, together with Yuval Perez, we generalize this so-called dimensional gap and prove the existence of such a constant epsilon 0 that for any probability matrix P, the Hausdorff dimension of the measure mu with independent but not necessarily identically distributed continuum fraction digits doesn't exceed such a number. It was non-linear IFS, but even for linear case, we consider infinite stochastic vector and consider a countable family of contractions. This contraction satisfies the so-called open set condition. And such a infinite countable IFS generate open expansion and generate the corresponding probability measure. Here list of contraction ratios and here list of probabilities. And this naturally to ask about properties of such a random variable, properties of the spectrum and here the spectrum coincides with the attractor of the corresponding IFS, and more interesting about the fine fractal properties of the corresponding measure. And first, rather unexpected phenomena related to non-faithfulness. I would want to mention that during the conference Fractal Geometry in Stochastic 4, which was in Graceville 5 years ago, we discussed this matter with Petri Matila, with Kenneth Falconer, Lars Paulson, also with Karol Shimon, and in one-dimensional case it was impossible to produce at least one fine-coloring system which is non-faithful. And now we produce several rather more or less simple examples which demonstrate that non-faithfulness can appear even in one-dimensional case. And even in one-dimensional case, the infinite IFS generates a lot of open problems. The first theorem shows sufficient conditions for the family phi to be non-faithful. So if Qi decrease polynomially, then the corresponding family is non-faithful. The following theorem shows that if corresponding stochastic element of corresponding stochastic vector decrease more or less regularly, at least in such a way, or if such a condition holds, then the corresponding family phi of cylindrical set will be faithful. I would like to mention here that until now we don't know necessary and sufficient conditions for the faithfulness, respect non-faithfulness of the corresponding family of phi. Related concerning the problem of fractal properties of the spectrum. If we consider the above-mentioned random variable, and we start with the case of IID. So here psi1, psi2, and so on are independent and identically distributed random variables taking such a value with the corresponding probabilities. To start the investigate topological support of spectrum of the measure is actually equivalent to the investigation of special set which are defined in terms of the corresponding Q infinity expansion for real numbers. Here we fix a subset V of positive integers, and any digits from this expansion should belong to this set V. This set can be considered as a special infinite dimensional generalization of Cantor sets. Okay, in the one-dimensional case, in the finite-dimensional case, as I mentioned before, the corresponding set should be the root of such an equation. But in our case, it's not true. And generally speaking, the Hausdorff dimension doesn't coincide with such a root. It is easy to consider for if Qi is defined in such a way, it is rather trivial to see that the corresponding equation has no positive roots on the unit interval at all. Okay, and the first theorem, if the corresponding equation has a root, corresponding equation has a root if and only if the corresponding series converges for any positive I. Okay, and if the infinite stochastic vector Q infinity and a fixed subset are chosen in such a way that the corresponding equation has no roots, then the Hausdorff dimension of the spectrum can be calculated in the following way. So we use the so-called cutting arguments to obtain this limiting result. I'd like to mention that the Hausdorff-Bezikovich dimension is extremely sensitive to any limiting procedures. So this result is rather non-trivial. And we have two cases. The first case, if the equation has a root, then this root should coincide with the Hausdorff dimension. In the opposite case, it is necessary to obtain a limiting procedure. But to unify both of this theorem, we obtain the following results. The Hausdorff dimension of the spectrum of the measure can be calculated in the following way. So we consider all x such an inequality holds, and consider supremum of all corresponding x. I would like to stress your attention to maybe to the simplest situation. For the IID case, let H be the entropy of the corresponding probability vector, and B can be considered the relative entropy of the vector Pi with respect to the vector Q infinity. And if such a condition holds, then by using both, by using ergodic theory approach or by using more or less traditional theoretical probability theory arguments, it is possible to prove exact formula for the Hausdorff-Vizikovic dimension of probability measure. So we obtain dimension for the minimal dimensional support. But what can one say about the Hausdorff dimension if such a series diverges? Actually, we discussed this problem with Yuval Perez several years ago, but and some ideas were how to generalize more or less traditional ergodic theorem to the case of infinite entropy, but this question is still open. Maybe Anatoly Katov has some ideas how to generalize traditional ergodic theorem for the case of infinite entropy. So if you consider functions not from L1, but such as the corresponding integral, non-integrable functions, maybe some cutting-edge arguments. Actually, I try to find corresponding theory. Well, I think this question may be interesting not only from the point of probability theory and fractal analysis, but also some motivation to develop general theory of ergodic theorems. For the case, if for the non-IID case, of course, non-IID case, the so-called general independent case, this problem more complicated, but under additional assumptions is rather technical assumptions. We also able to calculate the Hausdorff dimension of this corresponding measure. Probability theory for fractal analysis of singular measure to obtain lim-inf of such an expression. This number can be considered as a special relative entropy of distribution with respect to Lebesgue measure. But it is an open question whether is it true without such an additional assumptions. But I would like to mention that such an assumption, of course, is rather restrictive, but nevertheless, it is possible to use such a not complete, maybe theorem, not final variant of the theorem, to study some interesting problem related to number theory, the so-called normal numbers, non-normal numbers in different systems of numeration. And the last topic I would like just to mention, because in Friday, Irena Harkol and Marina will discuss more thoroughly about these things. So if we consider mapping R1 from R1 to R1 for simplicity, mapping phi, and the mapping phi is said to be dp transformation. So dp transformation means the transformation preserving the Hausdorff dimension. By definition, if Hausdorff dimension of a set E coincides with the Hausdorff dimension of a set H, where I is phi of E. And actually, a lot of already mentioned result and the corresponding metric and ergodic theory of different expansion can be considered in the following way. If you start with some general expansion, F is and you obtain the answer here some phi star expansion. And if the transformation phi presume the Lebesgue measure, then actually the metric theory of these two expansions should be the same. And it is not necessary to develop new metric theory of different expansion. And if expansion phi is dp, so if this transformation preserves the Hausdorff with the Polish dimension, then the corresponding fractal theory of the corresponding expansion should be the same as known expansion. So actually, by using such results I mentioned during my doctorate book, and by using dp, maybe it is possible to obtain many interesting and known from other point of view expansion like Lurot, modified Lurot expansion, and many others which are already discussed in a famous book by Fritz Schweiger. Okay, I'll stop my talk. Thank you.
Any questions, comments?
In connection with the ergodic theorem, you mentioned the infinite entropy. What is infinite entropy? Is this in thermodynamic sense?
But
I think it's just distribution.
if you have a stochastic vector, so the entropy of such a stochastic vector is defined as just metric entropy of stochastic vector.
So it has nothing to do with thermodynamic entropy?
Yes.
And how do you get infinity out of it?
So,
In thermodynamics,
do you want an example for infinite entropies? So, for instance, if Qi I part this constant, yes? And so, in such a case, the entropy will be infinite. Because the corresponding series should converge, but if you calculate the entropy, it should be infinite.
Well, for example, if you take an ideal gas, can you say that entropy is infinite when it's finite temperature?
No. Actually, it's a complicated question how to explain the notion of infinite entropy in physical sense. In mathematical sense, it is more or less clear, but I don't know how it can be interpreted in terms of physicals, in physics terminology.
I'm thinking of entropy in physics, and I'm a physicist.
Yes.
So when you say infinite entropy, I'm really puzzled. I don't know what it means. We must be talking about different concepts.
Sure. And since you mentioned this problem, I would like also mention some problem. It is more or less known notion due to Ruel and Bowen, the so-called thermodynamical formalism. And such a very, very nice procedure valid for a huge family of probability measures. But for the case I discussed for infinite IFS, this thermodynamical formalism failed in general. And it is an open question how to deal with such a measure.
More question?
Have you more complete description of DP transformation?
More complex?
No, more complete.
Complete.
Okay. Actually, the family of DP transformation is rather large family. Actually, it is known the so-called Klein approach to geometry, and any geometry can be considered as a mathematical discipline studying invariance of special group. For instance, affine geometry study invariance of affine transformation. Projective geometry, the corresponding topology study invariance of group of homomorphisms. But Kenneth Falconer suggested to consider fractal geometry as a mathematical discipline studying invariance of the group of the so-called by-Lipschitz transformations. So by-Lipschitz transformations such that from the matrix space M rho and C1 and positive. And actually, any transformation which are by Lipschitz is surely will be DP transformations. But if you want to classify the whole family, then it is almost impossible. Because, for instance, even in one-dimensional case, it is possible to construct a function f such that first f is dp, the second the set where the usual derivative is equal to plus infinity is of full Hausdorff dimension. And thirdly, the set n0 point x such that usual derivative is equal to 0 is also full. So rather complicated example. Of course, any function which such property is not by Lipschitz, but nevertheless it could be proved that such a transformation preserves a Hausdorff dimension. And this family is relatively unstable even after obtaining a convex combination. If you have two functions f1 and f2, which are strictly increasing, and dp, the average of such two functions, not necessarily dp function. But the development of theory of dp transformation is very important from very applied point of view. So if you have very complicated set, and if you map into more or less good set or less complicated set, and if the mapping is dp, that it is enough to calculate the Hausdorff dimension of more simple set. In many situations, such a trick is really wrong.
We have no time, so I suggest to discuss more questions in personal communication. Thank you again.